Hello, my name is Sarah Branham. I attended Destin Sandlin's November 28th lecture on how helicopters work. So I learned a variety of life and physics lessons from attending this lecture. Some examples of the physics lessons are the fact that chickens' heads stay still because of their vestibulo-ocular reflex. Additionally, that coiling honey produces a 17th order differential equation with 9 boundary conditions. And how helicopters work. I learned that swash plates can translate non-rotating motion to rotating motion. They're controlled by the collective and the cyclic. And my primary takeaway was that helicopter pilots are basically magicians because gyroscopic precession makes everything significantly more difficult due to the fact that pilots constantly have to account for different errors. So that was cool. Some things that I actually was familiar with were PID controls, or proportional integral derivative controllers, and I actually used PID controls in a robot that I built, where we were trying to have the robot automatically correct the path and that sort of thing, so that was kind of why I was familiar with that. And then the second thing that I was familiar with was when he talked about how cats land on their feet because they are non-holonomic systems. And I actually came across this while researching the gyroscopes used in the Hubble Space Telescope. So this is the area of focus that I decided to kind of expand upon. So the reason that this was interesting to me was because I'm really interested in space and how the Hubble Space Telescope works. I knew that it went through a ridiculous number of gyroscopes, and NASA spent millions and millions of dollars constantly replacing them, so I was just kind of interested in why they felt the need to do that. I learned that gyroscopes actually had 4 different beams circling at like 100 and something RPM, and they actually rotate in this sort of like motor oil fluid, and then the detections in the fluid are like how you navigate. So that was interesting. And then I expanded on non-holonomic systems. So these systems do not have non-integrable paths. So in traditional systems, we can kind of just rely on the initial and the final position, and then we know the orientation of our object depending on like how far it moved. However, with non-holonomic systems, we also have to take into account the trajectory because, for example, with spheres, the trajectory that you take can kind of can differentiate like how much it rolls, and then that'll change its orientation. So the initial and final position isn't all that matters in that instance. The takeaway from this is that they do not obey conservation principles, and therefore they're just fundamentally different. You can approximate them with traditional routes, however, you will have an error if you don't take trajectory into account. You can model linear non-holonomic systems using Lagrange equations of the second kind with multipliers. I kind of just came across Lagrange's name, which is a little familiar. And then one example of this is the Foucault pendulum. Definitely not saying that right, but this is basically like the initial pendulum was like a 200-foot pendulum with a huge mass on the end. And the way that it works is that in the reference frame of the Earth, the pendulum behaves completely normally, and it swoops back and forth. It has different maximum, and then it'll turn around and behave the way we expect a traditional pendulum to behave. However, because the pendulum is so long, we can kind of take into account the pendulum's behavior from the reference point of the sun. And because its path from peak to peak is so long, the Earth will rotate a specific amount. So the pendulum starts in the middle and then swoops up to the top. By the time it reaches its other maximum, the Earth will have rotated. And that gets back to the non-holonomic system and the trajectory, because the trajectory and the rotation of the Earth kind of like shapes how the pendulum moves in the reference frame of the sun, which is interesting and very cool. So this is kind of my takeaway in my research following Destin Sandlin's lecture. I thought it was really interesting and was very happy that I attended. Thank you.